Okay, so first problem, that is show that the sequence fn of x is equal to sin nx by n converges uniformly to 0 where x belongs to R. Okay, now proof, that is what they told that we have to show that the sequence converges uniformly to 0. That means, what is the definition of uniform convergence? Uniform convergence definition is, for each epsilon greater than 0 there exists a natural number n naught such that mod fn of x minus less than epsilon for all x belongs to S and n is greater than or equal to 0. That means by using this definition we have to show that it is uniform convergent. Okay, so we write, for each epsilon greater than 0 there exists a natural number n naught such that mod fn of x minus f of x is less than epsilon for all x belongs to S and n belongs to x belongs to S and n greater than or equal to capital N naught. This is the definition of uniform convergent. Okay, by using this definition we have to show this fn of x is convergent. Okay, so first we write, by definition, for each epsilon greater than 0 there exists a natural number n naught such that, what we have to consider here, we have to consider mod fn of x minus f of x. Okay, first we have to consider mod fn of x minus f of x, that is equal to mod, what is our fn of x given? Fn of x given is sin nx by n. So we write mod sin nx by n minus, he told that it converges to 0, therefore our f of x is equal to 0. So we write mod sin nx by n equal minus 0. Okay, so now this is equal to mod sin nx by n. So now if apply mod separately, we get this is equal to mod sin nx by mod n. Since we know that mod sin nx is always less than or equal to 1. Since mod sin nx is less than or equal to 1, this is less than or equal to 1 by n. Therefore, we got mod fn of x minus f of x is less than or equal to 1 by n. Now we know that mod fn of x minus f of x is less than epsilon. This implies, what is our mod fn of x minus f of x? That is 1 by n. 1 by n is less than epsilon. This implies, now write what is your n? This implies n is greater than 1 by epsilon. Now we got n is greater than 1 by epsilon. Therefore we choose n naught to be the positive integer just greater than 1 by epsilon. Okay, therefore we can tell that mod fn of x minus therefore we can tell that mod fn of x minus f of x is less than epsilon for all x belongs to R and n is greater than or equal to n naught. Okay, so this implies limit n tends to infinity fn of x is equal to f of x. Therefore we can tell that therefore the sequence fn of x is converges uniformly. The sequence fn of x converges uniformly. Why it is converges uniformly? Because n naught value, this is our n naught value. When you compare n is greater than or equal to 1 by epsilon and n is greater than or equal to n naught, our n naught value is 1 by epsilon. Therefore n naught value is depending only on epsilon, therefore it is uniformly convergent. Okay, so n naught value depending on epsilon and it is independent of x. Okay, since it is independent of x and it is depending on epsilon, therefore it is uniformly convergent. We know that if it is uniformly convergent, converges implies it is pointwise convergence. Therefore you can tell that therefore the sequence fn of x is equal to the sequence sin nx by n pointwise convergent. It is uniform convergent as well as it is pointwise convergent. Okay, this is the first problem. Next problem, second problem. Let fn of x be defined as fn of x. You can write this as a note point, this point as a note point. Since we know that it is uniformly convergent, therefore it will be pointwise convergent. Therefore the above example is also a pointwise convergent. Okay, so now take down this second example, that is let fn of x be defined as fn of x is equal to x by n for all x belongs to R. Okay, now apply. Since in this question we don't have what is our f of x, so first we need to calculate our f of x, then only we can check whether it is pointwise convergent or uniform convergent. Okay, so to get our f of x, what we have to do is we have to apply limit for the given function. So limit fn of x is equal to limit x by n. Okay, as n tends to infinity. Okay, so as limit n tends to infinity, x by n, as n tends to infinity, 1 by n will be equal to 0. Therefore this is equal to 0. This is equal to f of x. Okay, therefore this is equal to f of x. So consider, now we have to consider by the definition of uniform convergent, consider mod fn of x minus f of x. is equal to mod, what is our fn of x? Fn of x is x by n. X by n minus, what is our f of x? F of x is equal to, f of x value we got it as 0. Therefore, it is 0. So, this is equal to mod x by n. So, that is mod fn of x minus f of x is equal to x by n. So, this is equal to x by n. Okay. So, now what we have to do? Now mod fn of x minus f of x is less than epsilon. This implies, now what is mod fn of x minus f of x from this? The mod fn of x minus f of x is x by n. X by n is less than epsilon. This implies, now find the value of n. So when you are finding the value of n, we write this as n by x is greater than epsilon, 1 by epsilon. Okay, now this implies n is greater than x by epsilon. Okay, now choose n naught to be a positive integer just greater than x by epsilon. This implies mod fn of x minus f of x is less than epsilon. This implies limit n tends to infinity, f of x, fn of x is equal to f of x. Therefore, we write the sequence fn of x is pointwise convergent. It is pointwise convergent because n naught is depending on epsilon and x. Okay, since our n naught is, what is our n naught value? X by epsilon. Our n naught value is x by epsilon. That means it is depending on x as well as epsilon. Therefore, it is pointwise convergent. To be uniform convergent, it should be depending only on epsilon. It should be independent of x. But here it is depending on x as well as epsilon. Therefore, it is pointwise convergent. Therefore, you can tell that the sequence fn of x is not uniformly convergent. Okay, thank you, ma. This is about two problems. We discuss more one problem in another video.